Hello and welcome to the lecture on chapter 23, where we're going to introduce complex numbers for AC analysis. So some of the topics we're going to look at is the real number line and then the imaginary operator. And just so you know, if you've taken a math class and it is the I, in electronics we use the J so it doesn't get confused with the current. So we use I for current. So the J is the same thing. And then we're going to talk about how to work with the different number systems, whether it's polar or rectangular. And then we'll talk about impedance, and then we'll go through all the calculations and some of the shortcuts. All right, so in DC, there is no phase association, right? Everything is linear. So we're only concerned with the magnitude of the electrical quantities, and the values only have magnitude, right? They don't have a direction. Whereas with AC, they do. And because AC has both an angle and a direction, we're going to have to use complex. So let's look here, and if we just say our standard X and Y coordinate system, right? In DC, everything is just on the here, right? So like say I'm talking about resistance, if I have 2K of resistance, it's going to show up on the real number line here. Whereas with AC, I'm going to have my resistance here, and then my inductive reactance here, and my capacitive reactance there. So this will be, right? So my resistance can be here, and then my reactance is either, with an inductor, it's positive 90 degrees, right? This angle here, or a negative 90 there. So AC is going to kind of change things up a little bit. So we'll come back to that in just a moment. But this makes complex numbers very useful. So remember that, and then the term impedance is the total opposition. So impedance is the Z equals the resistance plus the reactance, whether it's capacitive or inductive reactance. So when we start looking at calculation this, we're going to have to deal with real numbers and then imaginary numbers. Okay? So that's kind of where we're leading up to. That's what we're going to get to. So the impedance is the total opposition to the current flow. And impedance can be either purely resistive, purely reactive, or both. So for example, and I know I'm switching back and forth between my camera and here. So this would be my resistance, this would be my reactance, with my capacitive reactance in the negative and my inductive reactance in the positive. So if I have a phasor, right? A phasor is a line that shows both the direction and the angle. And here, the angle is 0 degrees. This angle is 90 degrees. And this is negative 90 degrees, right down there. So if I have my resistance is this phasor, and then my reactance would be that phasor. Okay? And then this if I connect these, so this is my resistive part, this is my reactive part, and then this part is known as the impedance. So the impedance is going to have a phasor angle, which will have a magnitude, and then it will have an angle here, which is theta. The angle we're going to use is theta. And the angle is referenced from 0 degrees up. Now it can be negative, right? If I had a phasor here in the bottom part, this angle would be a negative angle. This is positive, this is negative. Okay? But it's still going to have the same concept. It has a magnitude and a direction. And that's sometimes referred to as a vector as well. So a phasor, also called a vector, is a quantity that has both a magnitude and a direction with the phase angle made with respect to a reference, which for us will always be 0. We'll reference 0. Okay? Now, the length of an arrow represents its magnitude, while the direction represents a phase angle. And we're going to use two forms of complex numbers. The polar, which is just a phasor, in which the magnitude and phase angle are expressed in angular form. So a magnitude of 7.07 and an angle of 45 degrees is a polar form. We can also look at this with the rectangular form, where we can express it with the real part and the imaginary part. Okay? Now, another form is the rectangular, which is based on the Gaussian or the Cartesian coordinate system, right? The XY axis. And instead of using I for imaginary numbers, we use J for electronics. Now, we're going to need to become familiar with some basic trigonometry to do some of these calculations. So, in our trig, right, and you're not expected to be a math major at this point in your electronics career, but you will have to take some math in your general ed. But the real part is x, the imaginary part is y, and then the impedance is r. So if we were to look at this in our electronics format, we would have the x-axis here, our impedance here, so that's our reactance, so we'll say it's x of L. This is our resistance, and then this part is our impedance, and here is our angle theta. Okay? And this is all going to be based on trig. And with trigonometry, you can calculate the sine is the opposite, or y, over the hypotenuse. The cosine is the adjacent, or x, over the hypotenuse, and then the tangent is the opposite over the adjacent. So that's how you can calculate that. And in this week's homework, there'll be some questions that will have you do that. So you just have to refer back to this and then do the calculation. And I'll show you how to do that here in a second. Okay? So keep that in mind. Now, sine, cosine, and tangent are called trigonometric functions, and because similar triangles have proportional sides, the values depend only on the size of theta and not on the particular triangle. So we can write polar as the phasor, right? That's this magnitude at this angle. We can also write it in rectangular, where we say the real part is here, and then the imaginary part is there. So both are saying the same thing. So how do you calculate that? How do you get those values? Well, to do that, you have to look at the idea of, and I'm going to skip over this imaginary number stuff. You can read it in the textbook, and then I have it here in the slides. But for us, we're going to say that what we're interested in is the relationship with the real numbers and the imaginary, and then converting from complex or from polar to rectangular and rectangular to polar. So, but first let's do an example here. So let's look at homework, the homework problem, the first one here. So it says calculate the values of cosine of theta, sine of theta, and tangent of theta when the opposite is 20, the adjacent is 12. So we need to calculate this r. And we know on a right triangle, so let's say this is 20, this is 12, this is theta. What is r? Well, we know that the Pythagorean theory says, we'll put it in our terms here, it's going to say r squared is going to equal x squared plus y squared. So let me just use these values here. So this is going to equal 12 squared plus 20 squared. Or r squared is going to equal 144 plus 400. Or r is going to equal the square root of 544, right? So let's use our calculator here. And so I'm going to just go back into normal mode. So we're going to say, what is 12 squared plus 20 squared is going to equal 12 squared plus 20 squared is going to equal 544. And then if I take the inverse of my answer, that will give me 23.3. So now I know that this value here is 23.324 or whatever you want to put there. Okay? So once I know that, I can then calculate whatever I want to calculate here. So let's do, so I'm just going to redraw this, and we'll say this is 20, this is 12, 23. And if I want to find the sine of theta, right, here's theta. If I want to get the sine of theta, it's just remember the sine is the opposite over the hypotenuse. So this is going to be opposite over 23.32. So if I take 20 divided by 23.32, I end up with a sine of 0.857. So this is 0.857. The cosine of theta is going to equal the adjacent over the hypotenuse, so 12 over 23.32. So if I take 12 divided by 23.32, I get 0.514. And then the tangent of theta is going to equal the opposite over the adjacent, so 20 over 12, which equals equals 1.667. All right. Now our calculator also has the arc tangent or the inverse tangent in the inverse sign in the inverse cosine. So if we wanted to find the angle associated with that, what is theta? We can take, so now we could take the inverse of that. So here, let's go. Well, I'll come back to the angle in a little bit. But for now, I just want to show you, that's how you do the basic trigonometry. And that's all you need to do. And so then on the second problem there, it says, calculate the length of side x given that the tangent of theta equals 0.4. So on that one, so here, let me draw that right here. So it says, here's our angle, and this is 15 centimeters. Here's theta, and here's x, right? We want to find out what x is. So to do that, we can do, here we know that the tangent of theta equals 0.4. So we know that tangent equals opposite over adjacent. So if we solve for the opposite, we're just going to say opposite is going to equal the tangent of theta times the adjacent. So then we'll just do 0.4, which is given, and then we know the adjacent is 15, and that's going to equal 6 centimeters. Okay, so all you have to do is look at the first page on that homework, and it will get you, you'll be able to answer the first 4 questions really, really easily. All right, so now let's look at this real numbers and the polar and rectangular. All right, and this part is really, really basic too, once you understand it. So in our calculations for addition or subtraction in rectangular form, you add or subtract the real and the j terms separately. All right, so this is straightforward. So if, let's say I have 9 minus 3j plus 7 plus and I'm gonna change this one. It's 9 minus j3 plus 7 plus 2 j2. Let me. So if this is what we're given, you can just write this right underneath it. And I know this brown pen is not the greatest, but 9 plus 7 is 16, and then negative j3 plus j2 is going to be minus j. So that's, to add and subtract, that's all you do, is you just literally add them up and subtract them. So let's say we have 21 plus j19 minus 13 plus j12. So 21 minus 13 is 8, and then 19 minus 12 is going to be j7, or 7j. Okay, so that's all you do when they're in rectangular format, you just add and subtract them. Now, so those are the real and the j terms separately. So this slide here shows you just take 8 plus j5 plus 5 plus j4 is just 8 plus 5 plus j5 plus j4, and so forth. And subtraction is the same way. And then you can do multiplications this way. If you take 8 times 5 plus 8 times j4 plus j5 times 5 plus j5 times j4, and then you get this negative j squared, and then you end up with the values there. Okay? But it's easier, and then division is there. But I'm going to tell you now, don't only add and subtract in the rectangular format, and then do your addition and subtraction in polar. So to do addition and subtraction in polar, you just, or multiplication and division in polar, you just take 16 times 8, and then you, in multiplication, you just add these angles together. So 16 times 8 is 128, and then 25 plus 51 is 76. And then in division, you subtract the numbers. So you still divide. 16 divided by 8 is 2, and then 25 minus 51 is negative 26. Okay? So let's do a couple of these on here. Okay? So again, I'm going to go to the homework so you can see some of these. Let me get my mouse over here. So here, let's do like number 8. It says negative 4 plus j 2.5 minus 6 minus j 4.6. Okay, so this is number 8 on the homework. So negative 4 minus 6 is negative 10, and then 2.5 minus 4.6 minus a minus 4.6 is plus j 7.1. Okay? And then while we're at it here, actually okay, and then let's do number we'll do number 6 here, which is, no, let me do number 7 because that's a polar. 7 says 8 at an angle of 42.8 times 2.5 at an angle of negative 25.3. So to do that, you just take 8 times 2.5, and then your angle will be 42.8 plus a negative 25.3, and you end up with 20 at an angle of 17.5. Okay, so number 7. So go through the homework and go through the questions in the back of the chapter, and it will help you understand how you can how to work with polar and rectangular. Okay, so now that we kind of have that under our belt, let's come into the idea of impedance. So impedance is the total opposition to the current flow in an AC circuit. Now it might be pure resistance, it might be pure reactance, or more than likely it's going to be a combination of the two. Okay, now the impedance of the symbol of impedance is the letter Z or zeta, and the unit of measurement is the ohm. So if we modify Ohm's law in the AC, we have the total impedance is going to equal the voltage, the source voltage, divided by the total current. Now, because the magnitude of impedance is the ratio between the voltage and current, the impedance has a phase angle associated with it. That is the difference between the voltage and the current phase angles. Okay? Now, in most AC circuit analysis, the source voltage has a reference angle of 0 degrees. Now, impedance has a negative or positive phase angle depending on whether the circuit is dominated by capacitance or inductance. Now, inductance will have a positive phase angle. Capacitance will have a negative phase angle. And the diagram will have R, X, and Z, where R is the resistance, X is the reactance, and Z is the impedance. Okay? So here is our inductive capacitance, or reactance, and then here is our capacitive reactance. And then with inductive, if we have an inductor, our phase angle is going to be positive. If we have a capacitor, our phase angle will be negative. So this is positive here. Okay? Now, the natural form for impedance is the rectangular form designated as R plus or minus J, the net reactance. Get tongue-tied there. So in a series inductive circuit, it's going to be R plus J X of L, and then in a capacitive circuit, it's going to be R minus J X of C. Now in polar form, impedance is designated as Z and then the angle theta, and is found by the conversion from rectangular to polar. Now, series and parallel impedance is calculated the same as series and parallel resistance. So that's the same for AC as it is DC. Now, the impedance triangle is going to be calculated with the A squared plus B squared equals C squared, which is Pythagorean's theorem. And then it's also going to be related to the trigonometry. Okay? So Z is going to equal R squared plus X squared. So where R is the resistance and X is the net reactance, and then the square root of that will give you your value there. So it's the same thing here as with Pythagorean, right? A squared plus B squared equals C squared, or C equals the square root of A squared plus B squared. Okay? So you can see that, and we did that earlier. Then theta represents the phase angle. So the phase angle is going to be found by the inverse tangent of the reactance divided by the resistance, or the opposite over the adjacent, right? Because remember, this is our resistance, this is our reactance. So the opposite is the X, and then the adjacent is our actual resistance. Okay? So for a series RL circuit, this angle is positive, whereas for a series RC circuit, the angle is going to be negative. So if it's capacitance, it's going to be negative. If it's inductance, it's going to be positive. Now, the conversion between polar and rectangular is, you can calculate that. So convert the rectangular coordinates 3 plus J4 to its polar equivalent. So to do that mathematically, you would say, what is Z? It's going to be 5. And then what is the angle? It's going to be the inverse tangent of 4 over 3. Remember, it's X over R. So you can get the, so that the value would be 5 with an angle of 53.1. Now note that theta is greater than 45 because X is greater than R. If R is greater than X, then theta is going to be less than 45. All right? So here's some steps that show you using the calculator to do that, the calculations that we just did here, okay, right here. Now, the calculator can also be used to convert from rectangular to polar. So here's where you again solve for the impedance, and then you do so that's the same formula there. Now, the impedance of zeta angle theta is the hypotenuse of a right triangle with the sides formed by the real and the x. Okay? Now, if you convert 5 angle 53.1 to rectangular, you would take r equals the zeta z times the cosine of theta, which you get 3, then x equals z times the sine of theta, which is 4. So 5 at an angle of 53.1 is 3 plus j4. Now I'm going to show you how to do this on the Sharp calculators. So on the Sharp calculator, the easiest method is to simply put the calculator into complex mode. And you do that by pressing mode, right? So you have the mode key here, and then you say 3, which will put it in complex mode. And then when this is done, the calculator defaults to the rectangular mode. So notice this rectangular mode says XY. Okay? Now to convert from rectangular to polar, you convert 3 plus J4. You first press mode and make sure you're in mode 3, and then you're going to put second function R0, which is the one above the 8. So if you look at R0, and you can't see that, let me kind of zoom in on that. And I'm going to turn on the light too. Oops, turn on the light. So you see that R0 above the 8? So what we're going to do is we're going to press second R0. So let me clear that. I'm going to turn it on. We're still in complex mode. So I'm going to go second 8, and then I'm going to put 8, and then which puts the calculator in polar form. Now enter 8, and then I, which is the FDX key. So the FDX key is right here. So I'm going to press that, and it will give me the I. Oh, let me go backspace here. I want to go 8 plus I, and then I want 4. And then if I hit enter, this will convert it to the values that I want. Okay, so let's do the one in the book. So this is second, and I'm going to go 8 plus, oh no, why am I doing 8? I'm going to go 3 plus I 4 and hit equals, and that gives me 5 with an angle of 53, right? Which is what we should get. So then to convert 5 angle 30 of 53.13, I'm going to go to the second 9, which will then change that from the XY. Now we're back in the XY format. So let me do that other one first. So second 8, and notice this is R0 here. When I go second 9, now I'm in polar format. So to go from rectangular, or convert the polar to rectangular, you have to be in the rectangular format here. When you're in the 8, that's the polar format, right? Which is the phasor and the angle. Okay, so I'm going to go back here to 9. Now I'm in the polar, and I'm going to convert hold on, what I do here. Okay, so now if I go 5 with an angle, which is the DMS key here, so if I press that DMS, I get that. Let me zoom back out so you can see a little bit more of these keystrokes at one shot. Now, this camera is a little tricky, but I'm going to go 5, and then the angle is 53.1, and then if I hit equal, it will show me the real part is 3, and the rectangular or the imaginary part is 4. Now this, because I didn't have enough values here, if I did 53.124, whatever it was, I would get 3 and 4 right on the dot. All right? So if you use your calculator to convert from one format to the other. Now, let's say I give you a question, say on the test 2, which is coming up. You'll get that next week in lab. So let's say I have 5 plus J3, and I want to add it to 6 at an angle of 73 degrees. Well, you can't do that, right? So what I would have to do, well, you can't do it easily, but you can convert this into its polar format. So let's do what we just did. So 6 angle 73 degrees is going to equal 1.75. So let's just write it here, 1.754 minus 5.73 J. So now I can do this one. I can say 5 plus J3 plus 1.75 minus 5.73, and I end up with 6.75 minus 2.73 J, right? So once you convert it from one format to the other, then you can do the math. Well, and remember, if it's in rectangular format, you want to get both of them in rectangular, then you can add and subtract them. If they're in polar format, then you can multiply and divide it by just multiplying the real part and the adding and subtracting the angle. All right, so that should be enough to get you started on this week's lab, or not this week's lab, this week's material. And if you have any questions, post it on the Ask the Professor or send me an email, and I can make other videos that will explain this even better. All right, so that should be enough to get you going, and I will see you later.